Login time as usual. You can go ahead. On here.
Okay, so hello everybody. This is the Dirac seminar for mathematical physics. We are back with a little technical issue, but not speaking about the last week. It was another story. And today we are very happy that our invitation has been accepted by Andrey Krutov, who actually asked me to volunteer on this seminar as the speaker after Spiros talk about cubic Dirac operator. And today it could be something quantumly deformed version of Spiros talk. Concretely speaking, cubic Dirac operator for U of SL2. So thanks for coming.
Thank you very much for introduction and the little speaker of the project. Always very nice. So yeah, in a way, we'll speak about some algebraic Dirac operators in the spirit of Spiros was about, and but for this project actually came from some geometrical sites. It was 4 years ago. Give credits to Andrey Krutov on the conference in Prague here for problem to look at these guys. So to some quantum deformation of non-commutative bialgebras.
Yeah, sure.
Yeah. So let's start. So first of all, it's a joint paper with Pavli Pandic. You can see there's already something on archive, and second version will appear soon. And I hope after solving, yeah, now we can finally proceed. So what we're going to contact? As I said, under following, we want to consider some analog of the following concept for quantum groups. So what's a non-commutative algebra? So suppose you have some Lie algebra G, and you consider tensor product of its universal enveloping algebra with the Clifford algebra of it. So that means that we taking not arbitrarily Lie algebra, we also requiring existence of non-invariant symmetric bilinear form on it, so we can speak about Clifford algebra. Yeah, I will try to. So now it's an algebra where our Dirac operator lives. So let's choose a basis and dual basis. Let's consider the corresponding generators of universal enveloping algebra and a Clifford algebra. Then we can look at this particular element. So it's like a Casimir split it in two parts. One part go to a quadratic Casimir to Clifford, one to universal enveloping. So it's our sum plus cubic term, which purely belongs to the Clifford algebra. And why I say that it's a Dirac operator? Because it have a very nice square. It's square to Casimir plus some constant, which could be expressed as a trace of Casimir in the adjoint representation of G. For example, for SL2, my Dirac operator look like that. So you can see this is kind of your form split into universal enveloping and Clifford parts. So I will recall that E and F dual and evaluation of H with itself give you 2. And
the no basis means the PBW basis.
The basis.
No,
it should be F. Sorry.
Basis. Okay.
Yeah, it's basis in.
Yes.
That's a bit of Moscow English, sorry. So you just take in and take a dual. Basically, how you construct Casimirs. Remember the same answer. So, and you have a nice square. So it's Casimir for SL2 and constant to basically the space. Okay, why one should care? First, it's one of the components how to build theory about Dirac homology, Wolfgang's conjecture, a bit of Spiros was speaking about relative cubic Dirac operators when you have a sum algebra. A passage from this picture to Spiros one, you should consider some embedding of two non-commutative file algebras, then it induces image of your Dirac operator for subalgebra, you take a difference, you recover your relative Dirac operators. Another important application came from geometry. It was a works by Andrey and Alexeyev about Cartan's model and equivariant homologies of some G manifold, and it was main geometrical motivation for us because we hope that our gadgets that we can quantize could be applied on the quantum, on the non-commutative geometry side. But there's also nice works by Constant about applications. Let me mention algebraic version of Barrow-Weyl theorem, multiplets of representations. There is also some connections with Toda chains, but I will not speak about it much, just to mention. It was previous attempts to construct some geometrically inspired Dirac operators in non-commutative geometry by a number of people. I just listed some of them, and from geometrical point of view, non-commutative geometry in the sense of cons, Dirac operators one of the important ingredients of spectral triple, which is an instance of non-commutative geometry. And some of this work was considering about Clifford algebras and quantum Clifford algebras, and I will speak about it a bit. And inspiring work of Čech and Mesland about gauge series on non-commutative principal bundles, some quantum Riemannian geometry. And first step, actually speaking about relative Dirac operator for SL2, was done in work of Pančić and Sonberg. But let's start our journey of QD4 in this. Yes?
Could I add a question?
Yeah.
You mentioned quantum principal bundles.
Mm-hmm.
I remember that your last talk was about such kind of list. So does it have something in common with your work?
It comes a bit in parallel, because this part of the series that I'm talking now, it's not yet good developed, so it's ready to meet its applications. So we finished some algebraic part of it. So next step should be but it will be some parallels with my previous talk. Okay, the little introduction to quantum groups. So we're looking at the world of Hopf algebras and my usual slides. So if you know what is an associative algebra and draw all axioms in terms of diagrams, then you know what is a co-associative co-algebra. So now instead of multiplication and a unit, you have a map that is a co-multiplication and co-unit that go in opposite sides, and you revert errors in all diagrams. You got axioms of co-associativity. And what is a Hopf algebra? It's an algebra, also co-algebra, plus a special map that called antipode, such that it satisfies the following rule, and it's also an anti-algebra map. And it will be our main hero. So, one of the simple examples of Hopf algebra, take some finite group, look at its group algebra. You have the following structure map. So you have a coproduct given by this, co-unit and antipode. Another example is a tensor algebra. And what is more important, it is a universal developing algebra or Lie algebra. So here you have a coproduct and co-unit and antipode given the same spirit as for tensor algebra. And so why you need coproducts? Basically, coproduct tells you how to act on the tensor product of representations. And existence of co-unit is just manifestation that your algebra has a trivial representation. So why? Yeah, I will use this Sweetler notation, but in this talk not so much. So if you don't remember it, it's fine. Why I spoke so much about Hopf algebras? Because we want to quantize Lie algebras, but they're rigid objects. By some definition, we know there is, by homological reasons, there is no non-trivial deformation of Lie algebras as Lie algebra, or if you look at the corresponding universal enveloping algebras, all deformation will be trivial. So that's why quantum groups are important, because they deform coproduct, they deform monoidal structure, this part, on the category of representations. And the first and simplest example of quantum group is quantized SL2. So I fix some complex number, which is not a root of unity, and consider quantized universal enveloping algebra generated by the following generators, modular relations. So you have a K which look like quantized H in your SL2, and E and F, which satisfies the following relation. So these two guys tell you that E has a weight 2, F has a weight -2, and this is deformation of our commutator. And what is more important, we have a Hopf algebra structure which is not co-commutative. You see, in the previous slide when I spoke about the just universal enveloping algebra of G, I will have just E tensor 1, 1 tensor E. But here I deform these guys. So it was done by Green from Jimbo in 80s, coming from universal scattering methods and highly inspired by physics. So it will be second main hero of our talk today. So we have one ingredient for deformation of this non-commutative Weyl algebra. So we have a quantized universal enveloping algebra. The second ingredient is something that should be quantum or Q-deformed Clifford algebra. Let's see how we can construct it. Maybe I will skip this part because it's just tell you what is relation with the classical SL2. So I wanted to also emphasize that representation theory of UQ of SL2 looks very much similar to the classical case. So there is a highest weight series. So if you have a highest integral weight for SL2, you can consider the corresponding Fermat modules with a formula given in a very similar manner to the classical case. These Fermat modules have maximal proper submodules if your weight is dominant. And that's how you obtain finite dimensional reducible representations. Just take this quotient, and moreover, this representation will have the same character formula. So they're pretty much straightforward quantization or deformation of representation theory of SL2. So if you remember how representation theory of SL2 looks like, then you know how to do it for UQ of SL2. There is subtle difference because you have twice many representations, but we will not speak about this extra one because they actually come from some representation of the group structure. So to start building my quantum Clifford algebra, I need a space on which I will build it. So classically it was G itself. Here, as you can see, we don't have G, we have some case F. But there is three-dimensional representations that look like is a quantization of the adjoint representation. You can see it in the following way. Any Hopf algebra admits right and left adjoint actions. For example, left action is given by this formula. Here, there's explicit formulas for all generators. And now if you consider the special set that lives inside of UQ of SL2 and denoted by D2 with 0 V minus, you will find that it's actually a three-dimensional irreducible representation with respect to this left adjoint action. And it has the same highest weight as adjoint representation of SL2, so we can think about it as a quantized adjoint representation. So we have a copy, a quantized copy of SL2 inside of our UQ of SL2.
Sorry, A1 and A2 in the, let's say, splitting of A.
It's a coproduct. You take a sums. So it's this split representation. So that coproduct will be, I don't know, x1, y1 plus x2, y2, and it will be coproduct, for example, of A. So instead of writing this sum, I voluntarily write it like that.
Okay.
Maybe I should have wrote it like that. But it's very typical, and sometimes it's very annoying when you see it for the first time. But it's just representing for this sums. I think it will not appear later. So. Okay, here is a module structure. You can see that it's almost a representation of a joint representation, but you put Q in the right place. Now, we have an analog of our joint representation. Now I want to speak about how to take tensor products, because what was the point of this non-commutative Weil algebra? It was also an algebra in category of G modules. So the structure maps in that algebra respect module structure. If you will take ordinary tensor product in the category of representation of USL2, then you will not get an algebra in this category. That's why you need this business of braided monoidal categories. So suppose we start with some monoidal category, which we usually will assume which is strict. A braiding on monoidal category is a natural transformation between functor authentic tensor product and its opposite, which satisfy a hexagonal diagram. In particular, if you assume that your monoidal category is strict, you will obtain Young-Baxter equation, and yeah, braided monoidal category is a category plus braiding. So the famous Young-Baxter equation appearing in some physical works on quantum integrability. And the right way to take tensor product in braided monoidal categories is the following. So you not just flip A and B between, don't use just a flip map, you use your braiding, because braiding tells you what is isomorphism between B tensor A and A tensor B. Because in regular tensor product, you just flip these two guys and apply multiplication maps. So some non-trivial part. So we now know what type of tensor products we should take. Examples of such things, for example, symmetric braided monoidal categories. It's when you braid in squares to identity. Example, just vector spaces. Or then using braiding, you can define symmetric and exterior algebras as quotient of tensor algebra generated by eigen subspaces of 1 and -1. The same you can do for super geometry, for super vector spaces. Now you're braiding and counts all the chains of parity. And you will see that you can define symmetric and exterior algebras in the super case in exactly the same manner. But unfortunately, it's not so easy to do it for quantum group, because the braiding is usually not symmetric. So the square of braiding is not identity, so you have multiple angle levels, not necessarily 1 and -1. There is a solution for that. So first of all, we have a braiding given on category of UQG modules by R matrix. And
sorry, what is this? One or R?
Type 1 representations.
One?
Yeah. So it's basically weight representations.
Mm-hmm.
So non-type 1, you will have Q to the power probably plus -1, but just think about type 1 is quantized finite dimensional representations or Fermat modules from the G.
So weighted representation.
Yeah. Okay, what is the problem here? For consider of modules over quantum group, eigenvalues of your braiding usually q to some powers. But we know that it's q to some power or plus minus q to some power. There is a solution. We can try to normalize this braiding to have a plus or minus eigenvalues, which was proposed by Bernstein and Zwitznagel about 20 years ago. Then this normalized braiding has a good eigenvalues, and we can speak about quantum exterior and symmetric algebras. This normalized braiding doesn't satisfy Yang-Baxter equation. In many cases, this quantum symmetric and exterior algebra will be smaller or bigger than the classical counterparts. But yeah, this is how we define exterior algebra. But the good news that if we will look for R matrix for quantum SL2 and look, construct the corresponding braiding from it, just you apply this R matrix, so you know how F, E, and F acts, and this Q to the power acts just by this multiplication, and you take a flip. If we will look for the corresponding braiding and normalized braiding for our quantized representation, and look for the corresponding quantum exterior algebra, then we can deduce that it has a classical dimension and the following commutation relations. So you see there is some funny q's, sometimes q square, not even equal to 0, but that's fine. That's what's happening. Now let's remember the following thing, that we can think about Clifford algebras as a feature deformations of exterior algebras. Let's try to apply this technique in this manner. But what we need some form, some invariant form, and non-degenerate invariant form. So what means to be invariant form for Hopf algebra A? So it should satisfy the following condition. If you rewrite it using the core product for universal enveloping algebra, you will get the classical notion for invariant form for Lie algebra. And again, we have a good news that for our quantized adjoint representation, we have such form. So we have now two ingredients to build our Clifford algebra. We have some exterior algebra and a form on the space on which we build our exterior algebra. So let's deform. Yeah, there's some simplicity, and here we define our highly non-commutative Q-deform Clifford algebra in the following way. Yeah, later I will denote just that to get all this data, because we will figure out that it's not so important to have all of this data. So it's a right algebra, it's an associative, it's in the category of UQ of SL2 modules. It also has Z2 grading, so it mimics all properties of the classical Clifford algebra. Now, here is the corresponding ideal. As usual, there's a problem. So we have some tensor algebra quotient by ideal, how we should find a good basis, and it turns out that, first of all, this Clifford algebra is very nice. It has a Poincare called fit basis, and it's easy to prove. In this basis, we have the following multiplication table. So you see that it's really a deformation of multiplication in that exterior, quantum exterior algebra, because if I will put this parameter C to 0, then I will recover relations in my quantum exterior algebra. And yeah, so highly scary object, many Q's now and there. So we use some theory of braided monoidal categories, some quantum Keating forms to build this non-commutative object. Let's try to study it from algebraic point of view. First of all, we can find that there is a non-scalar central element that squares non-scalar element that squares to scalar. Horrible scalar, but what we can do, that means that we can construct two orthogonal projections with respect to this game. And they give us two ideals, which means we have at least two modules, and we'll call them spin modules, S1 and S2. Here is the formulas for the spin module S1. And you can see that one of the ideals vanished on that, on these modules. Another maps is isomorphic actually to endomorphisms of this module. It happens here. So you can, let me show the difference in these two spin modules. It's only how V0 acts. It happens now with reverse ideals. What it means? It actually means that our quantum Clifford algebra is isomorphic to the direct sum of two endomorphisms algebras. And from classifications of simple central algebras, we know that if we have an algebra of endomorphisms or some of them, then it's a Clifford algebra. So, in fact, as an algebra, our quantum Clifford algebra is isomorphic to the classical Clifford algebra of SL2, and the explicit formulas are given here. So here is your relations for Clifford algebra of SL2, and here is this isomorphism. Let me know that we still need a module structure on this algebra. So when we start with just classical Clifford algebra, we don't know how UQ of SL2 will act on it. So the important piece of information that our quantum Clifford algebra carries, it's the action of our quantum group. So that's why I will continue using this symbol, telling you that, okay, I have a very special basis in my Clifford algebra, given by these formulas. Plus, I have an action of UQ of SL2. Because then I will be able to take these braided tensor products and speak about, is my future Dirac parameter invariant and stuff like that. So this quantum Clifford algebra is already classical Clifford algebra plus extra information about the action of your quantum group. Okay, now we're ready to construct non-commutative real algebra by the following recipe. So we take our quantized universal algebra, we take our Clifford algebra, quantum Clifford algebra, which carries the action, and take the braided tensor product with respect to braiding given by universal arithmetic. So that means that multiplication here is written like. So I should, before multiplying y and x, I should braid y and v. It's almost like in supergeometry when you have a sine rule with something of parity, something best with each other. Now, instead of simple sine rule, you have a more complicated braiding effect. The same idea.
And this braiding is the one.
Quasi-triangular.
Not the.
No. With Nadia Bernstein, you will have some problems because it doesn't satisfy the hexagonal equation, so it's very hard to make some iteration.
And you said something that I was a bit confused with. The exterior algebra that you constructed is from the standard quasi-triangular.
No, it's from
something.
Yes, because standard will give you some. Yeah. Okay. So now we have a place where our cubic Dirac operator should live. Yeah, that's recalling of the properties. A bit of notation. Just call. Let's consider these special elements in our quantum SL2. One of them C is a quantum Casimir operator, so it's element from the center of UQ of SL2. And then in such with such notation, we can consider the following element. So you can look at this guy, it should remind you Casimir part of cubic Dirac operator, because remember that x, z, and y, so x should be dual to v2, z should be dual to v0, y should be dual to v2, but with the corresponding constants. There is our cubic term, which squares to scalars, and some Casimir. Classically, we had one here, and I will explain you why it's not one, but in the limited period. What do we know about this guy? First theorem, that it squares to something central. So, again, we have not Casimir, but the square of Casimir plus constant. And some scary q integers, we can just forget about that. So we can now speak about this as a real Q deformation of cubic Dirac operators because it squares to the central element. Okay, now a bit of a comment how to see that it's have a good limit. We can, instead of this Casimir, we can consider another element from the center that have a nice limit when Q goes to 1. Because if you look at this guy and put Q equal to 1, you will have a problem with the commutator, with the denominator, sorry. This guy behaves a bit better. So when Q goes to 1, it gives you a Casimir operator for SL2. And in these terms, our cubic Dirac looks a bit bigger, but you can really see now that it's one tensor cubic term plus some deformation of 1 by quantum Casimir. And square of Dirac look like Casimir plus 1 plus again some deformation by square of Casimir. So it has a nice classical limit when Q goes to 1. Okay, let's continue studying of our gadgets. Star structures, because classically Dirac operators play an important role when you speak about some unitary representations of your Lie group. And if you have some real form of your Lie algebra, it gives you some star structure on universal enveloping algebra. And then if your Dirac operator is star invariant, then it's adjoined in the modules. So you can speak about some unitarity and try to solve problem with unitary duals of classical groups, which is not yet solved. And also you need that for some purpose of non-commutative geometry. So I will use this notation mainly for arithmetics. And depending, now suppose we have a Hopf algebra and have a universal arithmetics person. Depending on choice of structure, we can consider several cases. For example, arithmetics is called real when the following condition holds, and it's inverse real in this case. For quantum groups, it basically covers all possible star structure on quantum groups. And I also want to speak about star algebras in the category of modules of some Hopf algebra. So a star algebra is an algebra in the category of H modules if the following condition holds. Let's study case-based case. First, inverse real case. So R matrix satisfies the following formula. Then on this braided tensor product, it's actually a star algebra with respect to star map defined in the following manner. So we take stars of A and B, then added by R, and take a few. For quantum SL2, we have only one real form for which R matrix is of this type, is defined like that. So here Q lives on the unit circle, and it's denoted by SL2R. We can leave the corresponding formula for our Clifford algebra. It also becomes a star algebra, and we will denote it like that. And with a bit of calculation, one can see that our Dirac operator is invariant with respect to the star number. Good. Now, what about real case? In the real case, everything becomes much more complicated. It's quite surprising because a compact case belongs to this. We should consider now two braided objects. So, it's an easy exercise in the theory of R matrices that if you have an R matrix, then if you will take it in inverse and take a flip, which is denoted by R inverse to 1, then it will be also R matrix. So basically we have two different braiding. Braiding given by R matrix and by this guy. So it's actually a common symmetry of braided monodal categories, but I will not go too far in the category theory. So it's quite natural to look at these algebras and these two braided tensor products, and a priori you couldn't say which one is better, because you have no tools to choose. And now your star maps will be not mapped inside the algebra, but it will be pairs of maps between pairs of algebras. So they will still be anti-involutive, they will still be anti-algebra maps, they will be anti-linear maps, but now they not map from A minus to A minus or A plus to A plus, then it's maps between pairs of algebras. So let's denote two versions of non-commutative file algebras with respect to different braided tensor products by the following formulas. So we have plus and minus. Minus is a guy that we was considering before. What we can say about plus? Surprisingly, the plus guy also have a cubic element to central element. So you have a Casimir. In fact, it's the same element. But when you write it, they normally formally live in different algebras, but in these given bases, they coincide. Okay, which real forms we have for UQXL2 that cover this case? So it's a compact form, SU2. Then the corresponding real form of a Clifford algebra is given by the following formulas. And we have a US11. And I think I didn't wrote, Q here is a real number. Because I could already foresee the questions that, wait, Andrey, in the classical case, SL2 has only two real forms, either SU2 or SU11. But this guy SL2R is isomorphic to one of them. Here it's not happening because the previous real form was for values of Q on the unit circle. This guy for Q real. So it's algebra over different domains. They are not isomorphic by definition. Yeah, the corresponding real form of SQ11. And again, one could prove theorems that our Dirac operators, this pair of Dirac operators, behave nicely with the corresponding real forms. So for each real form, we have these pairs of algebras and star maps between them. And these Dirac operators are star invariant in this paired sense. Good. Now, that's a bit of an inspirational slide for a future, because I will not describe much here. There is a couple of nice works that give you a condition. So you have this scary braided tensor product. It's a nice thing because it remembers the action of your quasi-triangular Koch function. But what if you look at is as a just algebra? So in some cases, you can prove that this braided tensor product as an algebra is isomorphic to classical tensor products. And it's the case here. So there is exist map that embeds classical Clifford algebra of SL2 in this non-commutative file algebra, such that the following map is an isomorphism. And with respect to this isomorphism, we have a following nice decomposition of our cubic guy. What is good here? So we can clearly see that it's a classical cubic term, as I promised to you. So this is F, E, and H. They all live in the classical Clifford algebra. You have some scary coefficients that one should make sense to understand what is going on, but it looks like a typical generalization of this Dirac business to the case of outside of Lie algebra. For example, something like that happens with Dirac operators for Hecke algebras and stuff. So you're always looking at something tensored with a classical Clifford algebra. What is good about these scary coefficients between the classical coefficients? Well, first of all, they span four-dimensional representation. But now with respect to right adjoint action of UQSL2 on itself, and it's isomorphic to the trivial one plus its adjoint.
Just got a bit lost.
Yeah.
So I thought the definition of the quantum of W is just pretend what's on the left. I don't see where.
Well, no. Look, here it's a regular tensor product, not braided.
Okay.
So it's isomorphism of algebras, but not in the category of modules. So I don't know how to define an action here, because these guys, it's my classical Clifford. Okay. And that's why, for example, when you want to multiply here something like that, it's much easier because it's a regular tensor product. And you will probably ask what this coefficients means. Well, it's this guy. If you remember, Varanovich by covariant calculus leaves exactly this function. So it should be quantum tangent space for vectors, for plus or minus, I don't know. But it's probably a way how to generalize it for genealogy. Now, a bit closer to representation theory. So we want to define analogs of Dirac homology. That's why let's discuss representation theory of UQ of SL2 a bit in more details. So let's pick some complex number. Then we can consider as for SL2 type 1 Ver1 modules given as an infinite dimensional vector spaces with the following basis. And I believe, sorry for a typo, it should be W here instead of V, not to be confusing. Yeah, okay. So the formulas is Q deformation of the classical formulas. So if instead of these Q integers, I will just write regular integers, you will get a formulas for SL2 action. And again, if your weight is integral dominant, then you have a maximal proper subquotient, and it gives you finite dimension modules. You'll just quotient it, or by the same, assuming that the guys below is just equal to 0. Now, we want our Dirac operator to act on the module, on the tensor product of module for UQ of SL2 and some Clifford algebra, because it lives in the braided tensor product of UQ of SL2 and quantum Clifford algebra. So how to do it for these braided tensor products? Again, you use braiding to switch things. So suppose you have two structure maps for representation of two algebras A and B on two vector spaces. Then you can consider a structure map for an action of this braided tensor product in the following manner. Again, here you use braiding to swap these two guys, and then you act by A on B and by B on W. But before, we should switch things. So we will use this to define action of our non-commutative quantum non-commutative algebra on tensor product of our Verma modules and spin modules, and the same for finite dimensional guys. First, simple computation gives you this horrible formulas. Well, it's not so horrible. It's actually a page of computations, and somewhere here Q integers are hidden, but I just decided to leave it like that. So we want to speak about eigenvalues of these guys and spectrum. We see that for lambda not equal to 1, we have the following eigenvalues. So nice Q deformation of classical integers. The corresponding eigenvalues for Verma modules look like that. And the same happens for our finite dimensional guys. You can find these formulas in the paper, probably. The most important thing that we have a nice control how our Dirac operator acts there. We know we can nicely describe these eigenvalues. And in general, we can notice the following fact. So we know that our Casimir look like that. So on Verma module, it acts by the following scalar. That means the square of our Dirac operator. Remember, it's square of Casimir plus some constant. X as follows. That's why we can define first Dirac homology of some UQ of SL2 module by the following formula. So we take M tensor with one of the spin modules and then take the kernel of Dirac quotient by this thing. So remember that our Dirac squares to something central, so it's well defined. It's the same formula as you use in the classical representation theory. And we arrive to the following theorem. So the previous computation shows that for all finite dimensional and Verma modules, except one that has a weight, highest weight -1, the Dirac homology is 0. And a simple commutation shows that for this particular Verma module, you have a one-dimensional Dirac non-trivial homology, which perfectly generalizes the classical case.
Okay, okay. So also in the classical case, the homology is...
yes. This gets vanished, this one-dimensional.
Okay.
Okay, how much time do I have?
5 minutes. About 10 minutes.
Oh, 10 minutes. Should go pretty fast. Okay, maybe I actually will skip most of this and finish earlier. There's a part that's not yet finished, but I want to comment a bit of the connection of this business with the Lie algebras and Lie superalgebras. So it's a bit of a digression and trying to understand what is going on. Let's speak about the of a classification of semi-simple Lie superalgebras. Unfortunately, it's not so easy in the classical case. It's not just a direct sum of simple algebras. It's much more complicated. And here is a classification as obtained by Chen. So we start with some Grassmann algebra with n generators. It has a natural grading, just by degrees. Then you can consider algebra of derivations of this Grassmann algebra. And you can think about it as vector fields on 0 n-dimensional supermanifolds with polynomial coefficients. This vectorial Lie superalgebra has a natural Z2 grading just because Grassmann algebra is graded. So we have a partial derivative with respect to the generators. We'll have now degree -1. And let this guy denote the homogeneous component of degree -1. Now, any semi-simple Lie superalgebra, which means semi-simple in the classical works, that your radical is zero, is a direct sum of the following sums. So you take V is a some subalgebra of this vectorial of algebraic derivation of your Grassmann algebra, such that projection onto minus first component is onto, so you have all partial derivatives in your subalgebra. Then you start with some simple Lie superalgebra S and take some algebras that sandwich between your simple Lie algebra, Lie superalgebra, and the algebra of its derivation. And again, let me tell you that there is a particularity about super simple guys. They could admit some non-trivial exterior derivatives. That's why this guy is not just this. Why to care about this case? Well, because it looks like that when we look on this algebra, it turns out that it's pure deformation of this semi-simple Lie superalgebra. And one of the angles to attack this problem is to give a recipe how to quantize any semi-simple Lie superalgebra, which is not yet solved. There is a solution for simple guys, but not for semi-simple. So, or vice versa, maybe our work could give a light on such quantizations. Okay, thank you very much.
Time for questions.
So the exterior answer that you produced on the branching segmental exterior answer is, you said it was Koshul. Does this mean it's Frobenius as well?
Yeah. Yes, yes.
And could you put just a slide before this where you're talking, I got a bit confused.
About this,
No, maybe before this, where you're defining the adjoint.
Adjoint representation. What was here?
Yeah. So here you're talking about the action of the object of SO2 in itself being
Yes.
adjoint, and then below you're talking about the three-dimensional representation.
Yes.
But you're just using the symbol because this three-dimensional representation is not realized.
It's realized.
You're taking the one from Bordick, the realization inside.
Well, the formula is here. You start, it's the highest weight with respect to left adjoint action, so you can generate, you just act on E by
Yeah, now you scale your F so that then this is going to cancel them. Yeah.
And then I just redenote them. Yeah.
Okay, thanks.
And I don't know, from the point of view of this quantum exterior algebra, so you have this quantum object, right? But because we have this theorem, that these two algebras are isomorphic. But one can notice that filtration in these two algebras are different. So this map defines non-standard filtration on the classical Clifford algebra, which means that if you take now associated graded, you will obtain this quantum map. So somehow information about this quantum exterior algebra is already inside classical Clifford algebra. You just don't know the filtration.
But you can define the strength filtration on the CO2 as well, yeah, that it's isomorphism.
Yeah, but the main problem, we are looking for a recipe to do it in general case. Because it looks like overall comment is that one shouldn't care about constructing this Clifford algebra in the complicated way that I explained. This starting with this normalized braiding, building quantum stereo algebras which could not exist or give you a wrong dimension. No, you should just start with a definition that Clifford algebra is isomorphic to endomorphisms of spin modules. And you know that in classical case, spin module is also a G module. So you start with the corresponding quantum module state algebra of endomorphisms and work with it. There is a couple of problems that you should solve, and we are trying to do that. You need to define a filtration on these endomorphisms, because now it's much harder to do. Also, you need to identify a right copy of a joint representation, but that's a legitimate set of questions. And I think it will give you much, yeah, so we are working in that direction to generalize it for general G.
So your Q was kind of generic all the time, right?
Not root of unity.
No, so is there anything interesting?
For root of unity, it's work in progress, and I believe it should be something interesting, because there is a huge interest for centers of these guys.
Exactly.
So
yeah.
It's work in progress. I hope to present it maybe next year.
And like extending to others? Higher rank?
Yes.
It's some conceptual problem or just...
It's a conceptual problem. We don't know now how to guess this. Remember, always it was some horrible coefficients with Qs.
Yes.
We don't know yet, have a good interpretation of that. But it's probably because we don't know how, if we have a classical G vector space itself, how to embed it in a nice way into UPOG. So there is some set of ideas, but yeah. So we're working on it.
Somehow the fact that at some point you were able to express, is that correct? Dirac operator on square, using the generators of the
so
bicovariant calculus, does this help somehow for the hierarchy?
Not sure yet.
Not sure.
Because, okay, there it is.
Somehow whether you can see from beginning this bicovariant differential.
Yes.
Yeah.
So somehow we know that it's correspond to something probably in general case will be bicovariant, or I'm not yet sure, because bicovariant grows pretty fast. It's n square rank.
Yes.
Probably here we will need a joint representation plus Casimir or higher Casimir. So it's not yet decided. But then we need an embedding. So we know F. Now we can think about this as embedding of E star inside of UQ. This is H star, this is E star, and this is something that is not yet. So somehow we should answer our classical object in this case. So this is main conceptual problem now. And after we will find a solution, I guess we can define it in general.
Branimir had a question, had raised a hand, so.
Yes, thank you. Andrey, I had maybe a series of funny questions, possibly. Actually, maybe the basic question of all is, so this module V2 pi, and this may be a very silly question, is V2 pi going to be the module of left covariant one forms for the 3D calculus on SEQ2?
Well, it will be
Isomorphic.
as 3D, yes, because it's a quantized adjoint representation. I will, probably it will be tangent space for it. I should.
Tangent space. Okay.
It's not.
For the 3D calculus, it's not actually a module anymore. That's the problem.
Yeah. Sorry, it's misleading.
Yeah. It's a vector space.
It's a vector, as a vector space.
As a vector space, but so I mean, I guess the left covariant one forms are going to be then how is it going to go? The left covariant one forms are now going to define a left comodule for the adjoint. Sorry, I'm having a bit of my brain is not working today. So so there's no representation theoretic relation between V2 pi and the 3D calculus.
Okay.
As a module over the Cartan.
Yeah, it's just coincidence that it will be, well, this left covariant guys should be something that is quantized coadjoint. Yeah, so because basically it's a coincidence that as co-modules they'll be isomorphic, but nothing more.
So still as comodules. So they're still covariantly isomorphic.
Yes. If you speak about the co-invariant forms.
And and so the U1 action you get from K, I guess you'll still get a right U1 equivariant sort of. U1 will still work. So will it be identifiable in terms of the left SUQ2 coaction and the right U1 action?
Now I'm a bit lost. You're speaking about the U1 action on.
Because like the 3D calculus, it's not bicovariant.
Yes.
You still have this vestigial, like it's the structure group of the Q monopole. The vestigial right U1 action.
Yes.
And which still persists to the left covariant one forms.
I think it will be, yeah, it will be compatible.
So then, is the braided exterior algebra then going to be the left covariant differential forms of the 3D calculus? Or is the braiding different?
It should be.
But no, because you had the term that didn't square, that didn't wedge loop subscript 0.
I think it happens also for you.
See? I don't think so.
Well, Ray has a different opinion.
No, I think it's not. The 3D calculus, everything E wedge E is always 0.
Okay, I should check. But I highly suspect maybe they are isomorphic.
But it's not going to be something as simple as V naught corresponds to E naught and V plus or minus 2 corresponds to something times E plus or minus.
Maybe. I was sure that it's the same, but I just didn't had a look for this 3D calculus for a while, so I don't remember on the top of my mind, but I could check and email it.
Because if that is indeed the case, one thing that would be interesting is if this, so like quantum CP1 with the usual Kähler structure has its Hermitian metric, it's Hodge star and its Hermitian metric, etc. And this lifts canonically to the 3D calculus as the total space of the Q monopole. Outside Zampini and ansatz, you can fit it into general machinery, and in particular it gives you a Hermitian metric that is it has the suitable sort of its linearity and star properties up to the sort of modular phenomenon depending on the vertical horizontal bigrading. This is in the preprint I just put up. And in particular, your E naught E plus E minus will continue to be orthogonal. And so that makes me wonder, is there a choice of C so that your pairing you're getting, remembering that V minus is basically the star of v2, and v minus 2 is a star of v2, etc., and sort of thinking of it as a sesquilinear thing. I'm wondering if if you could choose a choice of C so that it actually lines up with this canonical lift of the Riemannian metric on Podlish.
Maybe I would be, yeah, it would be nice to see, because this parameter C is a bit mysterious, so it lives in the Laurent series in Q, and maybe it was missing some inspiration for a good choice of it. So that's why we keep that.
Because if this cubic Dirac admits an interpretation as a creature of the 3D calculus as the total space of the Q monopole, I mean, you could be back in a situation like the sort of the classical case of homogeneous spaces, where you have cubic Dirac splits up into a vertical bit plus a relative a relative bit, and then the relative bit descends to something downstairs on the homogeneous space.
Yes. Okay. We was thinking about this problem because for SL2 there is a relative Dirac for quantum SL2. It's Pablo and Pedro. I could send you the reference.
Please, thank you.
And one of the way how we was planning to attack it is via embedding of different Weyl algebras. So we will have a Weyl algebra for K, you embed it into a Weyl algebra for G, then you take a difference of your cubic Dirac for G and embedded cubic Dirac for K, and classically it gives you the relative Dirac operator. Cubic, non-cubic, it depends on the pair. So it was what I was thinking and keeping in mind. But now you're saying about some geometric interpretation. Yeah, that could be also nice to check.
Okay. And maybe just one other comment: if you're ever thinking ahead in terms of building a spectral triple-like thing out of this beast, the one thing I'd warn you is that up at this level, you should not be surprised if you inexorably get unbounded commutators with anything reasonable you do, because in this regime, when you lift up to 3D SEQ2, you have a perfectly reasonable Hodge-de-Ram. Like you're just going to get unbounded commutators for anything that faithfully represents any, the 3D calculus. It's just something you should expect. If you try to build a spectral triple-like thing out of this thing, you're going to get unbounded commutators, and you should not be alarmed.
Okay.
So that's all from me. Sorry to take up your time, and thank you for the great talk.
That's nice to speak to you.
Yeah.
Any other question? No? Thank you. Yeah?
Nice.
So, Brandon, yeah, I will check and then email you.
Oh, good. But please, thank you. Thank you.
Okay. Thanks
This is fun stuff.
for waking up.